Hi everyone, my name is Sophia Pambid, and I'll be presenting my project on estimating solar irradiance using machine learning. So a little bit about me. I was born and raised in the Philippines. Me and my family moved here in Hawaii back in 2017. I'm currently an electrical engineering student at UH Manoa with interest in power and renewable energy. So I decided to join this program to expand my skills as well as to discover potential career interests. Before this project was idealized, I knew that I wanted something involving a real world problem that aligned with my interest while also allowing me to get experience in machine learning. Hawaii aims to reach 100% renewable energy by 2045. So this presents engineering challenges. Solar irradiance, or the amount of sunlight energy reaching the surface, is an essential factor in photovoltaic power generation as well as energy planning, which brings me to my research question. Can machine learning be used to estimate solar irradiance from meteorological data? So to answer this question, I use data from Natural Energy Laboratory of Hawaii Authority. It's a CSV file containing the date, time, global horizontal irradiance, which is the total radiation on flat surface, as well as air temperature, relative humidity, and average wind speed. To process my data, I use different Python libraries, specifically for data analysis, visualization, and machine learning. I was also able to get additional guidance from the DataCamp modules and available Python library documentations. So before introducing the model, let's first understand the weather uncertainty. These plots represent different days. The yellow line is an ideal solar irradiance trend. So this is when there's perfect weather conditions, such as a clear sky. On the other hand, the blue line or the blue line shows multiple sudden changes due to change in weather, such as quick passing clouds. So this demonstrates the complex and nonlinear patterns of irradiance. I analyzed the weather variables and the correlation scores. The visual on the right displays these correlation scores between the variables and irradiance. A value of 1.0 is a strong positive correlation, and a negative 1.0 is a strong negative correlation. This confirms or this helped me verify the relevance of each weather variable before I use them as my training inputs. This scatter plot allows us to visually understand the patterns and relationships. Here we can see that the irradiance become larger as the temperature increases. The dot color representing the relative humidity also become darker in higher temperatures, meaning it decreases at high temperatures. On the other hand, the dot sizes don't follow a clear pattern, as you can see from the plot. So this confirms the low correlation score that I got from the previous slide. The model uses random forest. It creates many different decision trees where it looks at weather conditions and then produces a unique result. And then each of these results are then combined to form the final irradiance estimation. Random forests produce accurate estimations for large data sets and also reduces overfitting, which is basically memorizing instead of understanding the patterns. Here, I utilized the train test split from scikit-learn for data splitting and model evaluation. The old model only used the weather conditions as its training inputs. However, after adding the sun position and time lags, I was able to get improved results. Here shows the actual and estimated irradiance values side by side. The R squared value shows that the model is able to capture about 93% of the pattern. The median absolute error or the typical minute error is about 20 watts per square meter. And lastly, the mean absolute percentage error or the average error is about 12.7%. This plot represents the model's performance. The blue line is the actual irradiance values, and then the orange dashed line is the estimated values by the model. So following the timeline, you can see that the orange line follows the blue line. However, there are times where the model kind of overestimates or underestimates, especially in cases where there's sudden changes over the span of minutes. This is usually caused by passing clouds, as I mentioned earlier. So the main takeaway is that machine learning can be used to accurately estimate solar irradiance from weather conditions, and refining the features or training inputs can lead to improved results. As for future directions, I would like to expand this research by using data from other locations across the islands and also applying long short-term memory for further improvements. This project was an incredible learning experience for me. Through this research, I have learned how to use different Python libraries and kind of build on my beginner skills on Python, and also learning how to create data visualizations and having a foundational knowledge of machine learning. I would like to thank my mentors, Luke, Kayapuni, and Aftab, for your support and guidance throughout my research, and also Dr. Alex Stokes, NSF, for supporting this program, and also other more in the SCIPE program who made this possible. Thank you. Any questions?
Thanks very much.